Imagine I handed you a list of every single stock price on the New York Stock Exchange, or the population of every village, town, and city on Earth, or the surface area of every river, the street addresses in your city, or even just the numbers appearing in today's newspaper. If I asked you to look at just the very first digit of all those numbers, not including zero, and tell me which digit appears most often, what would you guess? Your gut instinct probably says it doesn't matter. There are 9 possible first digits, 1, 2, 3, all the way to 9. Since the numbers are random, each digit should appear roughly 11% of the time. It seems obvious. It seems intuitive. But your intuition is fundamentally wrong. We live in a universe governed by a hidden, silent mathematical architecture. In almost every data set you can imagine, the numbers are not random. There is a ghost in the system. The number 1 doesn't appear 11% of the time. In our reality, 1 appears as the first digit almost 30% of the time. In contrast, the number 9 only appears as the first digit 4% of the time. This means you are over 7 times more likely to find a 1 on a tax return than a 9. This is Benford's law, and it is the universal fingerprint that fraud investigators, the FBI, and data scientists use to catch the world's most dangerous liars. Look, this concept is deeply unsettling because it strikes at our understanding of randomness, but it works because liars are terrible at mathematics. If I asked you to fake a list of random expenses, say for a fake company, your brain is wired to make things look fair. You would invent numbers starting with 1, 2, 5, 8, and 9 evenly. You would produce a list where each first digit shows up around 11% of the time. You think you made a perfectly random lie. But when a forensic accountant looks at your data, they aren't looking at your numbers. They are comparing your numbers to the mathematical structure of the universe. When they see your even distribution, they know immediately that the data is fake. Benford's law is the only law in existence that a criminal cannot help but break. To understand why 1 dominates our reality, we have to look back to the late 1800s. It wasn't discovered by a cop or a math professor. It was discovered by an astronomer named Simon Newcomb, who was just trying to do his homework. In the days before computers and calculators, scientists used logarithm books to do heavy math. Newcomb was flipping through one of these massive books when he noticed something strange. The pages at the beginning of the book, the pages with numbers starting with 1, 2, and 3, were unbelievably filthy. They were covered in fingerprints, smudges, and dirt. But the pages at the end of the book, with numbers starting with 8 and 9, were pristine and white. Newcomb realized his colleagues weren't just working on random projects. The universe itself was forcing them to start with small numbers more often than large ones. Newcomb published a paper on it, but it was ahead of its time, and it was completely ignored. 57 years later, a physicist at General Electric named Frank Benford noticed the exact same thing. But unlike Newcomb, Benford was obsessed. He decided to test this crazy idea. He collected over 20,000 data sets, population statistics, mortality rates, street addresses, the surface area of molecular structures, even the first digit of numbers from newspapers. When he plotted them all, they formed a perfect, predictable curve. It didn't matter what the data was, it only mattered that the data was natural. So why? Why is the universe biased towards smaller numbers? The answer is how we process growth. We do not count linearly. We count in percentages of change. Let me give you a mental framework to make this physically make sense. We're going to look at how a number grows. Imagine you have a tiny savings account with just $10 in it. $10. Your target is to get your first digit to a 2. How do you do that? You have to make the number grow to $20. That requires a 100% return on your money. You have to double your wealth just to change that 1 to a 2. Now you have $20. Your next goal is to change that 2 to a 3. Do you have to double your money again? No. You only need to grow by 50% to get to $30. Now look at the other end. You finally have $90. How do you get that 9 to change? You need to get to $100. That only requires a tiny 11% growth to transition away from 9 and back to 1. Look at the board. You spend a massive amount of time waiting to grow from 1 to 2, but you only spend a tiny fraction of that time growing from 9 to 10. The numbers at the beginning of the scale, 1, 2, 3, are like massive plateaus we spend a long time on. The numbers at the end, 7, 8, 9, are just short speed bumps we fly right over. Benford's law applies to any data that covers multiple orders of magnitude and can grow exponentially, like stock prices, populations, and finances. If your data doesn't grow, like human height, we all start with 5 or 6 feet, the law won't work. But if the data is free to expand, the mathematical ghost always appears. This is the power of Benford fingerprint. In the early 1990s, the forensic accountant Mark Negrini began to apply this concept to detect fraud. A massive company's accounting should perfectly align with the Benford curve. If a CEO decides to skim $20,000 off the top, they don't just write one $20,000 expense. That is too obvious. Instead, they make 100 smaller expenses, say $298, $315, $387. These numbers seem random, but when a computer analyzes the thousands of expenses in the company's books, it doesn't see randomness. It sees that the fraudulent data has created a massive spike in the numbers 2 and 3, breaking the smooth Benford curve. The accountants know exactly where to start digging. This math has been used to detect tax evasion, scientific data fabrication in pharmaceutical trials, and it has even been used as evidence to challenge presidential election results. If you change a single digit in a single vote, you might ripple through the entire dataset and erase the mathematical ghost. What this proves fundamentally is that reality is not an accident. The structure of the numbers we find in nature, in finance, and in our societies is not random. The numbers themselves are evidence of a deeper architecture. When we try to cheat, when we try to lie, we're not just breaking human laws, we're breaking the laws of probability and geometry. The universe keeps perfect books, and if your numbers don't have the standard Benford fingerprint, the universe knows you're lying. You think you have free will, that your address, your stock choice, or your river's length is unique, but you are just a single point on a magnificent, predictable mathematical curve. Stop trusting your gut when it comes to randomness. The ghost in the numbers sees everything.